Welcome to This Explainer. We're diving straight into a scenario today that completely shifted how we think about remote monitoring. Picture this, August 26, 2026. The remote Nepal-Tibet border. A massive glacier collapses without any warning.
It really forces us to ask a chilling question. When 1,400 people go missing in just 7 minutes, what if we could have actually seen it coming?
The human cost of this event was absolutely devastating. 472 lives were lost due to the Langtang Lirung Peak glacier collapse.
Over 1,400 people vanished almost instantly, buried under ice and rock that was tearing down the mountain at 50 meters per second. Literally nowhere to run.
And the most terrifying part? This entire catastrophe unfolded in just 7 minutes. But, it wasn't human reaction time that failed us here. It was the total, utter lack of monitoring nodes in that remote area. We were flying completely blind.
So how do we fix this? Today we'll cover the harsh lessons from this glacier collapse, the communication dilemma in extreme environments, the breakthrough of chip fingerprints known as FACS PUF, disaster prevention with drone swarms, how this acts as a quantum hardware trust route, and finally, bringing this tech into the real world.
Part 1, the harsh lessons of the glacier collapse and the ultimate failure of our infrastructure. You see, traditional sensing networks heavily rely on wired communications and ground infrastructure. But here's the catch. The places where disasters hit hardest are exactly where those infrastructures are the most fragile or just don't exist at all. Remote mountains simply cannot support wired sensors. Satellites often fail or get blocked right after disaster. And international rescue? It's just way too slow to beat a 7-minute clock.
Which brings us to Part 2, the communication dilemma in extreme environments, and the critical need for decentralization.
Facing these brutal environments, we're basically forced to rethink everything. We can't rely on traditional sensing networks because they're vulnerable, power-hungry, and entirely dependent on ground wires. Instead, we need a system that can operate autonomously right in a disaster zone, totally independent of ground comms. We're talking about a completely decentralized approach, using FACS PUF autonomous nodes.
Moving to Part 3, chip fingerprints. FACS, PUF, the unclonable identity. Okay, so what exactly is a PUF? Under the Fully Analog Computing System, or FACS architecture, PUF stands for Physical Unclonable Function. During the manufacturing of any chip, there are unavoidable, microscopic physical differences. PUF leverages those tiny quirks to generate a unique, unforgeable device fingerprint. Think of it exactly like a human fingerprint, but for a silicon chip. It is an inherent physical trait, not just a string of software code that a hacker can easily copy and paste. Because it's hardware-based, it doesn't even need to store any security keys. It generates its fingerprint in real time, making it incredibly resistant to physical cloning. But the absolute game changer here, it runs on ultra-low power, less than 50 milliwatts. That makes it perfect for autonomous drones or tiny CubeSats. You don't need to establish a complex trust network beforehand. The moment you deploy it, it's trusted. And in a disaster zone or deep space, that kind of speed is literally a lifesaver.
To put it simply, quantum key distribution, or QKD, ensures the letter isn't read. But PUF ensures the mailman is real.
Part 4, disaster prevention and drone rescue, seeing this deployment in action. Let's look at how this plays out in the real world. Before a disaster even hits, we pre-deploy these PUF sensor nodes in mountain riverbeds. Every single blip of seismic or water data is authenticated right at the source, completely preventing any false alarms or data tampering. Then, post-disaster, when the ground network is wiped out, swarms of search and rescue drones equipped with PUF take over. The command center can instantly verify the authenticity of every single drone. So in massive, chaotic collaborations, you're guaranteed that absolutely no hostile or hacked devices are sneaking into the rescue fleet.
Now, Part 5. The hardware trust route for quantum communication, securing the final mile.
2026 isn't just about disaster recovery. It's a massive milestone year for global quantum communication. We've seen Starground CVQKD verify feasibility under a staggering 41 decibel loss. The UK successfully launched the ESPO QSAT CubeSat. The EU tested the world's first quantum-secured drone, and the ESA is actively developing their QKD set. And what connects all of these? FACS PUF technology acts as the missing hardware trust route for every single one of these projects. The quantum comms secure the transmission, and the PUF secures the terminal device. Together, they finally lock down that last mile of security.
Which brings us to our final section, Part 6, bringing the technology into the real world. A call to integrators.
We aren't just talking about a theoretical white paper anymore. The math models? Done. The virtual fab simulations? Done. The hardware mapping is completely finished. The technology is genuinely ready to go. What we urgently need right now are partners. We're calling on analog and RFIC design firms, as well as aerospace system integrators, to help us execute a 40-nanometer CMOS tape-out. We need your expertise to physically build this and bring it into the real world where it can save lives.
I want to leave you with one final provocative thought to chew on. With this architecture, chips don't compute the answer, chips become the answer. If you're as excited about this deep tech breakthrough as we are, please reach out to us. We would absolutely love to collaborate. Thanks for joining this explainer, and we'll catch you next time.